Hey guys, this is Thatcher and welcome to episode 6 of my DCTL coding tutorial series. To be upfront, if you're already familiar with C and structs, then you can probably skip this episode, but I find that structs are very useful when I code up DCTLs myself, so I thought it would be a useful thing to share with everyone who is maybe less familiar with C as a language. So in today's lesson, we're going to be looking at the tone mapping DCTL from lesson 2, and we're going to be adding one more constraint to it. The problem I had with our old tone mapping implementation was that you didn't really have a good way to control contrast that's going to be in your image. So as a starting point, I've copied and pasted the DCTL from lesson 2 over here and renamed it to DCTL tutorial 6, tone mapping. And I've brought it into Fusion already just to show you kind of the problem that I wanted to highlight. So here we are in Fusion, and let me walk you through my node graph that I have right now. So I've got my media in, which is a Zcam Zlog2 clip, which I've transformed into Ace's AP0 linear. Afterwards, I have our tone mapping DCTL, and I have a simple color space transform that goes from Ace's AP0 to Rec 709 Gamma 24. And you'll see that I have the tone mapping and gamut mapping turned off and the forward OOTF turned on. So here I have our tone mapping DCTL at the default parameters, and we can see that it's more or less doing the right thing, and it makes a fairly appealing result if we're being honest. I'm going to turn on my exposure chart and make sure we're monitoring the image that's after the tone mapping step. And what I'd like to highlight is that if we raise the black point, for example, as we raise it up, the slope at around mid-gray definitely flattens out. Now, that might be something that's desirable. Maybe it's not desirable. It's kind of subjective whether or not that's ideal or not. But what I'd like to do is to be able to control the slope at mid-gray. That way, if this overall curve is looking a little funky due to maybe a suboptimal black point or a suboptimal white point, then I can just tweak the slope that I'm choosing, or I could tweak the mid-gray point. But it's better that we can choose what the slope is than let the DCTL just choose on its own. As you guys will remember from episode 2, this was the slide that I showed that had all the different math that we needed in order to preserve these 3 constraints. Let's go ahead and add one more constraint. Suppose the user specifies s, the slope at mid-gray. In this case, then we're going to want the slope of our function to be equal to s when x is equal to the input mid-gray value. I've gone ahead and actually augmented g of x, our tone mapping curve, to be h of x. H of x is simply g, except I feed in a different value for x. The way this works is I'm going to scale x by the reciprocal of the mid-gray value. That way, mid-gray is mapped to 1.0. And then I'll raise this quantity to a power called gamma. As you guys remember from using resolve, the gamma wheel preserves pure black and 1.0, which is typically white. As a result, applying this operation of raising this quantity to the power of gamma will not move our new mid-gray point at 1.0. Finally, we'll restore our old mid-gray value by scaling the result back down to mid-gray. I've taken this whole expression and replaced it in for x within g of x to give us h of x, which is this entire expression here. To give us just a little bit of intuition, I've built out h of x and g of x within our graphing calculator tool. Here we can see g of x. This is the same function that we were using in episode 2 of our series. I'm going to turn on h of x, which currently has a gamma of 1. As a result, with a gamma of 1, this entire quantity is unchanged. For the purpose of this graphing calculator, I've renamed gamma to big Y because they're a similar shape. But just know that this represents gamma in my math. If I increase the gamma, then you can see that the curve will preserve mid-gray, but reach our desired white point faster than before. As a result, gamma gives us the capability to control the slope at the point that is mid-gray. I don't want to spend too much time walking through the math here, but the overall methodology was that I took the derivative of h with respect to x, evaluated at the input mid-gray, and then I set that equal to s, the desired slope at this point. This simply involved applying the chain rule for derivatives and then solving for s. Let's go ahead and add this new parameter s and our new constants gamma and our new formulation for h to our tone mapping DCTL. I'll first write out the parameter that we're going to need. Now, let's go ahead and write in a comment what we have to do in order to support this new constraint. All right, let's start by computing the value of gamma. Now we have to modify our tone mapping function, Tonemap_f3. We'll notice that if we now want to implement h of x, we have these additional parameters, the input mid-gray as well as the gamma. We also have to add these two parameters down here. Next, let's make sure that when we call tone map, we are passing in our mid-gray and the gamma. All right. Next, all we have to do is modify the logic of this function. I think I'm going to begin by making a temporary variable. Let's call it u that represents this quantity. And I'll substitute u in this expression. And finally, let's make sure that when we call Tonemap_f3, we are passing in this mid-gray and gamma value. All right. Let's see if this DCTL works. I'll copy it into my LUT folder and hit reload. We can see that it is still tone mapping, so the DCTL has correctly compiled. And now we'll see if the slope computation is making the right kind of adjustment. We can see that increasing the slope means that there's more contrast and that we can distinguish between fewer stops within our exposure chart. And likewise, reducing it means that we can see a lot more stops within our exposure chart. So there we have it. We could just call it a day right now. But you'll notice there's something slightly inconvenient when we're trying to implement this code. Over here, we're modifying two functions, ToneMap and Tonemap_f3. These two functions have basically the same parameters, but if we're being honest, Tonemap_f3 doesn't really care what the parameters are. Every time I want to modify the original ToneMap function and add more parameters, I have to modify Tonemap_f3. What I often do in my DCTLs is if a function has a lot of parameters, I'll group those parameters together into what's called a struct. Let's see how that works. In order to store these 5 different floats, I'm going to use what's called a struct in C. Struct is short for structure. A structure is a data type in C that allows you to access different members of possibly different types in an organized way. So let's go through an example of this. I want to make a struct that contains all of these parameters here, other than x. I'm going to define a struct using the word struct and open some curly braces. And then I'm going to write each of the member declarations. Whenever I have a variable that has this type, I will be able to access its members A, B, C, mid-gray in, and gamma, which will all be floats in this case. You can see each of these member definitions includes a type of that member as well as the member name. And we can assign to each of these 5 different members when we create and use a variable whose type is this kind of struct. In order to make this actually useful, I am going to use the keyword called typedef, which means type definition. The way typedef works is it allows you to assign a name to a type that you've created or a type that already exists. For example, in some kinds of code, you might find it convenient to refer to an unsigned char as a byte. In those cases, you would write typedef unsigned char, and then you'd write byte. In this case, unsigned char is some existing type, and then byte is a name that I've assigned to it. Now, byte doesn't have to be capitalized. It could simply be lowercase like this. So what we're going to do down here is we're going to define this struct to be the type, and then we're going to rename it to be something else. So I'm going to call this whole struct here tone map params. I like to use _t to indicate that it's a type. Okay, let's go ahead and use this new type to keep our parameters organized for these different functions. Within our transform function, once we have figured out what all our different parameters are going to be, we can start off by declaring our parameters struct. I'm simply going to write. This line will allocate enough space for this kind of struct on the stack and point params to it. I believe by default it should be initialized to all zeros. However, regardless of what it's initialized as, we're going to override each of the values using A, B, C, gamma, and the mid-gray value. In this case, when we're accessing each member of params, we're going to use dot, like the period, and then use the name of that member that we had defined earlier within our struct. Next, let's pass params in instead of all of these different values. We're going to write params here. And then within Tonemap F3, instead of having these 5 different parameters that are of type float, we'll just have a single parameter of type Tonemap params t. Now, let's go ahead and pass params to the inner function here. And we can repeat the process with Tonemap. I'm going to have to replace each of these different old parameters with an access to the corresponding member of params. While we're here, we might as well update all of our comments. And let's go ahead and see if our new DCTL works. I'll hit reload, and we can see that it is indeed still working. This code has certain maintainability improvements over the old code. As an example, if we wanted to add our parameter mid-gray out, as well as white point and black point to our parameters object, then we would simply have to declare those down here. And then I could write those values to those members. And then now I don't even need to update the parameters of the function Tonemap F3. All these new values will be passed to Tonemap as members of params. And then it is simply up to Tonemap whether or not it wants to use those different parameters. Before we go, I want to highlight a couple other options that you have when it comes to writing code that's like this. Rather than using this fairly verbose way to initialize each of the different members of params, we could initialize it similarly to an array. That would look something like this. Here, we've used the curly braces and then indicated in an order that matches the order defined up here, each of the members of params. By declaring it in this way, this one line of code is now equivalent to what was previously 9 lines of code. Now, I will say that this more verbose version of this code is perhaps beneficial in that it's harder to make the mistake of assigning a member a variable that you didn't intend to assign to it. In other words, if I wrote out this initialization in the wrong order, then I could have bugs that are somewhat difficult to identify. Whereas it's easier to avoid that mistake if I write it out like this. Another thing to highlight is that depending on what system you're on, you can't reinitialize params in this way multiple times. So if I've declared params here, then I must use this curly brace notation to initialize all of params on the same line at which I declared it. I wouldn't be allowed to write params is equal to this, and then later assign it in this way, then later assign it again with different values. That wouldn't be allowed, at least on NVIDIA machines. And the last thing I'd like to notice is that we can actually use this struct as a return type for functions. Let's see what that might look like. First, let's go back to the old version of params that only had the parameters that were necessary for this function called Tonemap. I'll go ahead and delete our mid-gray out, white point, and black point, and also remove them up here. Next, let's suppose that we wanted to do all of this calculation within its own dedicated function. Let's write out what that might look like. We'll write device, and then ultimately we're going to return a tonemap params t object. We'll call the function calculate params. And this is going to be based off of the black point, the white point, the mid-gray value, and the slope. Let's go ahead and declare the tonemap params t struct that we intend on returning. And in between these two lines, we'll have to populate each member in out. We can do this by just recycling the code that we wrote earlier. And finally, we'll have to do mid-gray in. That should do the trick. And now we simply have to initialize params using our new calculate params function. Let's go ahead and remove this code. And there we go. Let's see if this code runs. It appears not to. Let's see what our problem is. Oh yeah. So of course we do have to update some of these other values here. So all these references to A, B, or C have to be replaced with out.a, out.b, and out.c. There we go. So in this example, we have improved the readability of our transform function. We've broken out the parameter calculation into its own dedicated function, and we've used the magic of structures to make our code more manageable, making it so that we don't need to update the list of parameters in many, many different places. And instead, we only have to update it in places where it's being used. This makes it so that Tonemap F3 is something that we don't have to touch for a long time in the future. All we have to do is update Tonemap and update our structure definition. So there we have it. In this lesson, we've covered adding one more kind of constraint to our tone mapping DCTL. And then we use structs and the typedef keyword in C in order to make our code easier to manage when we have an increasing quantity of parameters. If you made it through to the end of this episode, thanks so much for watching, and I'm excited to see you in the next episode of this DCTL coding tutorial series.